Hello, guys. Good morning. Can you hear me okay? Sound check. All right, guys. Very good.
Any event that we did a cross-validation analysis, are you gonna grade that or?
No, we're not grading this. The right. So this is more of a honor system. It's basically kind of the incentive for you guys is to submit the work. So you are taking, you are sort of, taking the initiative, right? Yeah. Because so right now I have like 70 people in the class. It's just not feasible for me to grade. So the reason so I do this is like, I share the work with you guys and also highlight some of the works, right? So you can sort of learn from each other. Yeah, yeah. So this is very how do you say, much more relaxed uh, environment. Yeah, we're not grading anybody. Yeah. So all right, guys. So anything else? Any other logistics questions, feedback? I hope this last 2 weeks gave you guys a chance to kind of take a break. We all need that, right? So and then also catch up on some work we were trying to catch up. Now, what I want to talk about quickly is let's review cross-validation because that's a very important topic. And so again, I sort of, I look at the right. So again, you can submit through Google Doc. So people you are turning in. So again, like I said, basically, I am not here to police you guys. So you are in charge of your right. How well you want to, how much you want to get out of this. So please submit as on your own time. Even if you're late, just submit, right? And then so other people can learn from this, and then you can learn from other people. So if you look at the week 13, I just made these, I just added these links, right? Class submission folders open. I saw some good submission. I really didn't have time to go through and kind of validate them. So thank you for submitting. So this is great. I'm going to walk you through some of the couple of my solutions. Okay. So same thing, right? You guys probably had the same thing. And also, I was kind of curious what kind of data you guys chose, right? I was kind of like looking at these. So I think Jenny, I think you chose the U.S. income data, census data. I believe that's a very good data. Yeah. And can you guys put it on your chat window? What data did you guys choose? I kind of want to see everybody to see it on your chat window. Maybe you can speak up to it. Just tell me what kind of data you guys chose and maybe a link to the data as well. Yeah. Because this one I kind of kept us open-ended, right? The yeah, okay, the heart condition, right? Exactly, yeah, right, yeah, very good, very good. So US census, okay, Richard, US census, okay, got you. VG driven data. If you don't mind, can you post the link to this also, please? Right, so everyone can kind of access it. Yeah. Oh yeah. So yesterday, I remember you were mentioning the astronaut data. What is this about? Let me see. So is it basically like the astronaut data? I'm looking at the JSON file here. Is it like classifying problem? As in like, if this person would make a good astronaut? Oh, I see. Okay. I see. Gotcha. Okay. Determines gender. Got it. Interesting. Okay. So they have all these physical traits. Gotcha. Interesting. Okay. I haven't seen this data before, so that's good. That's very good. And this is good, right? Because sometimes when I read blogs, they will say, oh, I'm using this data. And I'm like, oh, this looks like interesting data, right? I will go look at the data. And if it's interesting, usually I add them to a elephant scale data set because usually with the data sets, sometimes, links disappear, right? People take it down. So I cannot keep my own copy. I mean, if it's all public, right? If it's, we have permissions to use. So that's how I sort of collected the elephant scale data set, like one by one, right? So, all right, that's good. Yeah, this astronaut data looks pretty good. So thanks for this. What else? All right, let me see which is, this is disease spread. Interesting. Oh, cool. I haven't thought about, okay, driven data. So it's like a Kaggle-like website. Looks like they run competitions. Yeah, okay.
Correct. So, but they're open to use this data. So I was trying to make it public,
Yep,
and so
very
that
cool.
our,
Okay.
all our team can use it.
Yeah, that's perfect. Yeah, that's very good. Very good, yeah. Good deal, layers. Okay, sure. No, this is really good. And this is exactly the purpose, this is exactly why I didn't give you guys a data set, right? Because I know, like, if I did, everyone will be doing this. so, so I wanted you guys to find your own data set. And it looks like, yeah, it's pretty interesting data sets. Adult data set. So this is the income data set, I believe, right, Alan? The adult data set meaning the income over 50,000 or something. Is that right? From UCI, I believe, right? Yeah. Good, guys. So this is very good. Any other data sets you guys kind of used and or even looked at? Maybe you looked at a data set, but you didn't end up using it. Can you guys please put those links on the chat window for me? Any other data set you guys looked at, but not end up using? So one data set you can use, again, I haven't looked at this yet. The so I don't know if they still have it. So in US, when you make a campaign contribution, the data is public, right? So the organization that keeps track of this is called Federal Election Commission. So if you see 2020 contribution data or something, I don't know, sometimes they take a few months to upload, right? So if you go to them, and there's a place you can download the data. Again, they can keep, yeah, there you go, right? So you can sort of go look at the data, and you can actually download the data, right? So because it's all public, and right. So this makes a pretty good analytics because the data is kind of real world data, and you can extract some pretty good patterns out of this. So I would kind of put this one in, just right. I haven't looked at the latest data yet. Election spending. So use election spending data from FEC, right? So kind of yeah, and this is a really good exercise if you, especially when you're trying to master pandas, and also trying to understand do more advanced visualizations. This is a pretty good data set, right? Because you can end up doing like graphs like US state graphs and all this cool stuff. Yeah, so that's a good one too. So actually you're saying COVID-19 data set. Where are you getting it from? COVID-19 data set. Can you post a link? Oh, sorry, David, I see your link, but it's your local link. Yeah, not a it's your local computer. Do you have like a public URL? Because this is good for me too, guys. Because I mean, sometimes I look at the data, and sometimes I will add to our data set if that's that's really interesting to me, right? So I'm learning from you guys too. So
Um, You know what?
yeah,
The thing that I'm looking at is I think you can scan through many data sets to see which one is going to be more that's going to be more say scalable to you. But the thing is, supposedly you go to a data set in which like nearly like every row or every column has got a null value.
that's right. Yeah. And this is very true. The part of part of dealing with real world data set is a lot of the time you're going to be spending cleaning up the data, right? Now you made a good point. Like a lot of data sets will have a lot of null values. So now the simplest thing is drop all the null values. Now when you do this, you lose a lot of data, right? Especially in real world data, like you said, each row might have some null value somewhere, and you just drop all the rows, you'll end up losing a lot of data. So the next approach is, you can basically substitute another value for null, right? So I'm just an example. you can substitute like 0 for now, right? Just an example. But does it make sense for the data set? Like, for example, right? If somebody, like, if you have a weight column, right? For something like, let's say you have people data and you have weight column, 0 is not a valid number. Right? So then you say, okay, maybe if it's a null, I'm going to put like an average weight. Now, what's an average weight, right? Now, average weight is like, that differs from whether, whether you are a male or female and how old you are, right? So, then now you're sort of going into this rabbit hole. It'll say, okay, if the person is less than 10 years old and male, average weight is this. You know what I mean? You know what I'm saying? So you can actually spend a lot of time doing this, and this is what data scientists do. Like, they'll spend a lot of time kind of shaping and massaging the data. And to do this, you need to understand the data, right? Like I mentioned, right? I mean, for example, if you are looking at a weight column, then you would know, what 0 is not an acceptable default. And you can put it, you can put just one number either, because then you're like, okay, it's like male, female, at least you have to consider that, and then maybe age group, right? So you can sort of see this, right? Yeah. So there's no formula for this. Basically, just need to know the data. There's no shortcut, right? Yeah. You will develop some intuitions as you deal with more data. But like the example I mentioned, this is one of the cases I worked on. We had like some people data, and some other columns were empty. So we are going to come up with default values, and I can just put like default value 100, right? Because that's it. Then we are going to say, okay, look at this row. How old is this person, male or female? You know what I mean, right? And then based on this, we came up with some default value. Actually, we end up having like 20 or 25 default values, right? If this is the default value, right? So what I'm saying is, this is just one example, right? So now next time I see data like this, I will know, okay, yes, I remember, this is what we did earlier. So, you can sort of build on the experience. So the technique here is just, practicing, right? Kind of as you get more data, spend some time looking at the data, understanding data, right? There's no shortcut. That's a good question. Yeah, really, I'm really glad you asked me that. Yeah. What is HCV data? Let me look at this one, guys, real quick. Looking at, actually it's down one in the data. Okay, so let me see if I can open this up. Okay, I see. Yep. Okay, so this is the cholesterol, right? Okay, got you. Yeah, the heart disease data, right? Yeah, got you. And this is pretty cool, right? So when I look at the data right here, right, I like this data right away because it's all numbers. So I don't have to bother with encoding the data. And just looking at just glancing the data overall, looks like the data is pretty much all there. Right? So yeah, right. So these are good. So I mean, I really like these data set. I mean, I see like a couple of missing values here, and that's fine, right? But if I see like not all null values, a lot of empty cells, right? Then, right? Then I kind of say, okay, how can I clean this up? But I mean, this looks pretty decent. And also, you have like almost like 600 rows, right? So even if you end up dropping nulls, I don't think you lose a lot of data. Anyway, judgment calls, right? Everybody kind of makes their own judgment calls. So this is pretty good. So thanks, Vijay. Okay, so this is the COVID data I see from David. Let me check this one. Okay. CDC data is pretty good. But what I found is in the past is like sometimes you need like know the domain, right? Because they are very like very health focused data set, right? So you really need to kind of look at the data, understand the pattern, like what are they talking about to really understand data. Yeah, right. So this looks reasonably okay. Hospitalization, ICU, okay, yes or no, kind of. Yeah, that's pretty good. Yeah, this is very good, guys. Yeah, very nice. Cool, and I'm surprised to find they have like a nice visualizer right there on the website. Cool. So this is good, right? So I will, you guys can save this chat window. Do you guys see the chat message, right? You can just save all the chats, right? So this way, you have some really good data sets here. So good. All right, guys. Anything else? Anything else we should discuss? Sort of, finding a data set, right? Because this was like an open-ended lab, right? Anything else you guys encountered? Please, yeah. Let's discuss it.
Oh, I began to notice that when you look for COVID data, like on other websites, they have things like time series data like some of the spreadsheets that they give you are really going to be time series data,
Mhm.
or sometimes it's going to be already. I mean, sometimes you're lucky and you see already clean data.
Right.
Like they'll give you data, but the thing is that you kind of have to. But with finding COVID data, you got to be very careful with
Yeah.
what you use.
Right, like even here, right? This is like a time series data, like you sort of see here, right? When the case is admitted and all this, right? Time series data is a little tricky, right? Because because time is now you got to consider time as a factor as well. We will do some time series maybe towards the end of this course. Kind of we'll do like some more assignment based task, right? Because time series takes a little special care to process. So that's a good point. Yeah. So I'll put this as a to-do item on our list. We'll try to do a couple of time series labs. Yeah. So right now, I'm again, my hope is, guys, kind of right. So as we kind of go through all this, right? Now you guys should be fairly confident in algorithms, right? So and that's what cross-validation is coming in, because cross-validation basically is kind of elevates you from just looking at a single algorithm. You're like one level above now, right? You're kind of looking at multiple algorithms and able to evaluate, right? So that's what cross-validation is kind of, hopefully, you just get the idea of cross-validation, and we'll do a couple of labs here. So let me start with the labs, and we'll kind of come back to discussion too. So here, where's my right? Okay, there we go. That's my guide. So again, solution sub-posted, guys, right? And also, so I will start with mine, right? Like I said, just the reason I'm doing this because I haven't had time to look at your solutions. So I'll just go through mine real quick. So I have 3 notebooks I'm sharing with you guys. One is just a basic intro, like what is cross-validation and learning the API. And the other one, I'm doing cross-validation on a single algorithm, right? And the other one, I'm CV3, I'm evaluating multiple algorithms. Okay, so let me show you guys all 3. So let's start the basic, right? Again, I just simply clicked on it, right? And then you say open with Colab, right? And remember, when you guys open, when you guys open with yours, make sure you're saving it in your own directory, right? Because come on, go away. Right? So you can save the changes. Okay, so let me go here. So this one, you guys already know the basics of cross-validation, right? So let me bring up the, you guys already have the slide, so I'll just go through this real quick. Right. So with the cross-validation, why are we doing this? Okay. So kind of back to basics, right? When you get some data, we don't use all the data for training, all right? Because then you are left with no data to test with. If we use the exact same data for training and testing, the model can cheat and you have no way of knowing, right? So that's kind of the basics we are starting with. Then we said, okay, fine. We don't want to do everything. So let's do like let's keep something for testing. So we do like train test split. But how do we do the split? Randomly, right? Every time I run this, I get 80%, 800 samples randomly. 200 samples I keep randomly for testing. So now we are kind of random, right? As in like every run I do, and you guys have seen this when you do our labs, every run I do, you get different results. Because why? Every time we do, we get different training, different testing data. So there's a bit of a variation. And we can fix this, you guys know how we can fix this using setting the random state. But you're kind of fixing it, right? You're kind of basically, when you fix the random state, what are you doing? You're kind of, putting your thumb on the scale and saying, yeah, I kind of want to fix the randomness. So you're not really seeing the full picture. The reason we put the random state is so when you're debugging something, when you're changing, experimenting, you actually stabilize the randomness. So at least that's not changing, right? But that's not the final goal, right? Because it's like you kind of just choosing just one random state to test your model. You're kind of forcing it. So this is better than before, but this is not the final aim. And that's where cross-validation comes in, right? Because we kind of want to do random, but we want to do random systematically, right? So that's why. So cross-validation kind of goes like this, right? So basically what we do is we divide the data into multiple splits or multiple folds, as they are called. And we do runs, right? And then each run, we systematically change the data set, right? As you can, so you can see that, here the first, here the first split was the test data. Everything else was used for training. So when I do this, I get, let's say, I'm measuring accuracy, I get 1 accuracy, 80%. Next run, right? Next run, see the test data now changes, right? So now this becomes the test data. Everything else used for training. We run the thing, and then my accuracy is 84%. So every run I do, I'll get different accuracies. Because, right? Because the model is training on different data, and the model is tested on different data. So it's kind of like this, right? Imagine I have like 100 questions. I'm going to give you guys 80 questions to practice. And then I'm going to give you 20 questions to test your skill. And let's say I give this to like, let's say we run the same thing over and over again. And, every time I give you like different 80 questions, like 80 practice questions, and then, 20 test questions. So you're going to score, your score is going to be different, right? Because sometimes, you get very good training questions, so you learn a lot. Sometimes your training questions are not that great, so you don't learn a lot. But, but the test questions are harder, so, you don't score that much, right? So this is important to understand when you do training, testing, cross-validation. We do multiple runs, and each one you get a different accuracy. So at this point, I have a pretty good idea of the model. I can say, this model, we tested it systematically. This model can score anywhere from 80 to 90% accuracy. So if somebody really pressed you, say, okay, what's the accuracy? Give me like one number. You can say, let's just take an average, all right? And there, there are other consideration in this point as well, especially if you have like a very skewed data. But let's kind of table that for now. Let's say, if you really say, just give me one number, I'll say, I'll just do an average, 85%. Right? So that's basically cross-validation on a very simple scale. Does that make sense, guys? Do we understand the basic premise, right? Why we are doing this? Any questions on this one, guys? Mike, I see your question. I'll come back to this one. Yeah. Okay. So that's CV. So now that we understand this, let's go back and sort of look at some code samples. How do we do cross-validation? It's very simple, dead simple in scikit. All right. So first, I'm going to give you guys like a very simple, just demo. Right. So here, I'm creating just a range of numbers. Say 0 to 20, 25, just 25 numbers. Printing it out. Then what I'm doing is, right, I'm creating a fold. All right. So what this fold does, you can see, right? I am saying, do 5 splits, right? And I don't want to shuffle the data. I mean, keep the data order as it is, right? So this is my fold. Remember, so basically when I do k-fold, okay, let me bring this up here. Scikit. K-fold, right? You'll see the algorithm, right? Basically, right, you're saying, how many splits? So default is 5, right? And then whether you want to do shuffle or not. And also you can set random state. So, you guys now understand random state because, pretty much all, you can even fix the randomness here. But, we don't recommend this because, why, there's no point, right? Because, we are systematically doing this anyway. So we only fix random state if we're kind of debugging something. Usually we don't, right? So I say, okay, create 5 folds, right? That's the main thing. Right? All right. And then I say, okay, you know what? Split this data. So remember, I have like a, remember I have like an array of 25, right? We are splitting the data. So, and then I ran, I'm just running through, just bunch of, right? Bunch of iterations, right? And basically I'm simply printing out what's my training data, what's my testing data. That's it. Right? So I have 5 iterations. Why 5? Because I'm asking for 5 splits, right? Kind of like this, right? So here I'm doing 5 splits. So I'm doing 5 runs. So if you look at the data again, these are just random numbers, right? I mean, that's right, just a number of 0, 1, 2, 3. You can see the numbers here. These are my training data, right? And the testing data. And you can see every run is different. And one thing you guys will see is like, right, these numbers, see, we are systematically, like every number is systematically being tested using testing. See, 0 was tested here, right? And then 24 was tested, right? And the reason I didn't do shuffle because now we can actually look at the numbers, right? It will make sense because if I shuffled it, it will be all scrambled. And one thing you will see, right? So we have 20 observations, 5 iterations. For each iteration, right? There's no duplicate between training and testing. Either you are in the training set or you're in the testing set. You cannot have overlaps. Right? That is the that's a guarantee cross-validation makes, right? So when you split training and testing, there's no overlap. And also, every observation is testing only once. Take a look at this, right? Look at number 0. It only appears once. Look at number 21, only once. Why is this possible? Because remember, right? We move the data, so there's like the same, like, every time we run this, we use a different testing data, right? There's no overlap. And this is what cross-validation does for us, right? It'll look at the data, it'll do the, it'll split the data and do the right thing. Yeah. So this is like a very basic, like a, like an intro, how cross-validation works. Does it make sense, guys? Right? Right? How they do this? Because it's kind of, once you understand the, fundamental, applying it becomes very easy. Yeah. So that's basically, how cross-validation will work. And you can play around with this. You can sort of split this into, like, say, different shuffles, right? And play with different data and all that. Yeah. Right. So question was, how about this? How about the model cheating, right? So remember, the ring is each of these runs. These are different runs. So there's no previous memory. That's a good question, right? So the model doesn't remember the data from run 1, right? Like every run is like a clean slate. Yeah, exactly. That's why. Because otherwise, you're right. Because otherwise, and this I just ran into this last week. I was doing a deep learning class, and then we were training the model. And then what they did was, so because deep learning models take a long time to train, what they do is, as you're training, they save snapshots, right? So we changed something, and then I say, all right, guys, run it again. But then what happened was, it was picking up from the snapshot, and it was basically resuming from there. Right, so we didn't see the answer, and I was kind of wondering why is it doing this, and then I realized, this person had a snapshot turned on. Right, so what you had to do is, like, in that case, you had to basically go and, like, completely clear all the snapshots, right? So it has no memory, and then rerun the algorithm. Anyway, that's what I ended up doing. But yeah, in this here, you can say, yeah, each run there's no memory, right? It's like clean run from scratch. Yeah, because that's what you want, because you don't want model to remember any of the residual memory from the previous run, because then the model can start cheating. We don't want that, right? Because we want each of the runs to be independent runs as, yeah, right? So very good question. Yeah, is that gonna make sense? Yeah, does it explain? Yeah, very good. All right, guys. So that is basic cross-validation. All right. Now let's look at the next one. So next one, what I'm going to do, I'm going to do cross-validation on a single algorithm. All right. So let me look at this one. So same thing. No, this is the old one. Okay, this is the new one, right? So what I've done here is I just chosen I just chosen a very simple data we've been using, the college admission data, right? Because the point of data, this is not the data side of things. It's understanding the cross-validation, right? So what I've done is, right, I can so let me clear all the outputs so you can run through. Right, download data, read data. Again, all this is usual, right? So here basically I'm extracting X and Y. Remember, this is critical, right? Because at this point, again, this is luckily for me, it's all numbers. If you need to encode it, scale it, you know what I mean? All this happens before, right? And then you finally say, okay, here's my X and here's my Y, right? So, and then here, I sort of, did that, train test split, right? 70-30 split, and then I'm doing, logistic regression. Okay. Did I do that? Yeah. And then printing out the numbers, all the usual stuff. Again, this you guys have done many times. Confusion matrix, right? All that, and finally calculate the model, training and accuracy model, right? So 82%, 76%. All right. So now what I want you guys to do is like, so remember that like 80 to 76, right? So here if I run it again, see, changes, 74, 76. Run it again, different, 84 and 80. So what's happening? Because, right, we are doing a train test split, and when I do train test split, I'm not setting the random state, right? I'm completely letting it go random. So every run I do, I'm getting different values. Right? All right, so you can sort of, you can run this in a few times and take an average, right? But let's do it systematically, and this is where cross validation comes in, right? So if you look at this cross validation, okay, so here's a cross validation score, right? So let me show you guys, this is very simple. Can I ignore all this for now? All right. So here's my logic regression. I'm simply saying cross validation score, right? Okay, it's very simple. This is the algorithm, right? I'm testing my logistic regression algorithm. This is my X and Y. And I'm saying do 5-fold, right? 5 iterations, right? And what am I scoring on? Accuracy. That's it, right? This is the simplest form there is. And then when I run this, you will see, right? So it's the 5 runs, right? 1, 2, 3, 4, 5. And these are the accuracies I encountered. You can see, right? It's, I get 100% here, 90%, 50%, right? All over the place, right? And then say, all right, what's the average? All right, 79%, right? Let's say. So this is different than what we had before. Before, I was like, my thing was jumping all over, right? Every run was different. Now I have a decent idea of, I'm saying, it can go from anywhere 50% to like, 90, almost 100%. Pretty wide range, right? I want to see if they support something. 1 second. Yeah, okay. So here okay, yeah. So it's not, okay, yeah. So I was looking for something. I'm not finding it here. I'll explain on the next one, right? So is this kind of makes sense, guys, right? So you say, what? I don't want 5, maybe I want to do 10. Sure, right? 10 splits. All right, let's do it. Right. So again, but you see, right? The final score, remember the last one, like 79%, right? See, when you take an average, you get a much better result, right? So that's why, you're not getting like any wild result, like, before and after. So people ask me, so how many folds should I do? Typically, I mean, there's not like a right or wrong answer here. Typically 5 to 10, right? So as you can see, 5 is the default, right? If you look at this, the default will be, where's that? CV5, right? So it'll be 5. I remember the last one I showed you guys, yeah, that was 5, right? And a cross version 5 splits. That's the default. So the CV can be a number, or you can give it a k-fold as well. So when you do a k-fold, it gives you a little bit more flexibility, right? You can control how the data is shuffled and all this stuff, right? But honestly, guys, I just do number, right? Because to me, I just take all the default values, and then that's good enough, right? So is this step making sense? Right? I mean, right? Basically, the only difference is, right? What's my algorithm? Oh, and another thing here, right? Here we don't do. I am not giving training data. Remember in the early days, we kind of, we'll do the train test split, right? Train test split, and then train on the training data. Can you guys tell me why I'm not doing this? I'm just giving the entire X and Y to cross validation. Why am I not doing training data? Any guesses? What do you guys think? Why am I not doing training? That's right. Because remember, cross validation will split the data for me, right? So I don't need to do the train test split anymore. And we shouldn't either. You know why? Because we want the cross validation to go and systematically split the data across, like say 5 or 10 folds and test it, right? So one of the mistakes I see here a lot of the times is like people just give X train and Y train. I'll tell them there's no need, right? Because let cross validation do this for you. there's a way. I mean, okay. So having said this, now that we talk about this, I've seen some scenarios. People give only X-trained and Y-trained data, and the reason is very simple. Like, so imagine, let's say you're a company, right? You're hiring an outside company to do your data science project, right? Let's say you're running like maybe 2 or 3 outside projects, companies to build models, right? So you have 1,000 data points. That's all you have, right? Now, out of the 1,000, so let's say this is team 1, right? That's building one model. There's another team 2, right? You basically only give out 800 for the teams as a public data, and say, okay, you know what? All right, guys, here's the data. Go build this, right? So this is your public, this is your public data, right? And you keep 200 on your own. Now, from here, for these guys, right, they only got 800 data, right? So they will take and say, okay, we got 800 samples. Okay, maybe we do like a, whatever, right? 80-20 split. Let's train on like, something like, 701 or something. Let's say these guys train on 701, 100, and these guys train on like maybe 650 and 150, right? So they do their own split. And they submit their models. So let's say team 1 submits model 1, right? And team 2 submits model 2. Then you test this data on your secret 200 data, right? And then so let's say team 1 says, okay, guys, model 1, we are getting like 85% accuracy, right? They do the cross validation, we are saying, yeah, 85%. And team 2 submits and say, we get 80% accuracy, right? But in your secret data, model 1 scores, let's say 90%, right? And then this model scores maybe, let's say 70%, right? So this is your test case, because the reason you don't want to give this out is because you don't want other teams to cheat and somehow tweak the model for your data. You know what I mean? You kind of want them to build a generic model, right? That will actually work for your future data. So you're kind of keeping some data as secret, right? To do the final evaluation. Because if you give this out, teams can look at the data and maybe they can tweak the algorithms to fit the data, right? So they at this point, they're kind of manufacturing a model to fit your data, right? Not the other way around. So when you do a competition like Kaggle competition, right? This is what they do, right? They will give you some public data for you to train, right? And then we take the data and then we further subdivide into two, like training and testing. Because for us, this is all the data we have, right? Then we submit our solution, then Kaggle will test this on their own secret data, right? So this way, everybody has a pretty much a, how do you say, level playing field, right? Because since you don't see the data, you cannot cheat them, you cannot tweak the model to fit the data. Is it going to make sense, guys? Right? So in these scenarios I've seen, so now your data can split, 3 ways, right? You have like, like a 200, like a sort of secret data, right? Private data, I would say, private data. And then public data, you give this much out. And everybody takes this data, and then from here they do their own train test split and do the whole thing, whatever, right? Cross-validation and all that. Is that making sense, guys? Kind of understanding, right? Because sometimes you will see this happening as well. Yeah. So in that case, you will actually do, only give train data. But in our case, right, we actually want to use all the data. So that's why I'm giving X and Y. So I'm letting cross-validator to split the data on my behalf. Yeah, made sense? All right. All right, guys. So we did 5 runs, right? And this is the rate, right? We came up with this, right? Came up with the number, right? And then let's see. All right. So this is cross-validation score. This is the simplest thing to use. There's a more detailed one that's called cross-validate, and this kind of goes into more detail. So let me explain what this is. Again, I'll kind of comment this out because we're going to worry about this. Again, same. Here's my algorithm. So instead of scoring, I'm actually saying cross-validate. Same parameters, right? Algorithm, X and Y, my how many splits, and then what am I scoring on, right? Scoring metrics. But here, scoring metrics, you can see, right? I can have more than one. Because here I only had one, it's accuracy. here, remember, confusion matrix, we looked at accuracy, precision, recall, and all the stuff, right? You can give as many supported metrics. And then when you run this, right? So you print this out and see, we did 5 runs, right? So you should see like 5 runs, right? 1, 2, 3, 4, 5. And it'll also give you a lot more data. It'll say, how much time did it take for training? Fit time, right? And how much time for scoring, right? Scoring should be very quick. You can see, right? And training is something that takes, a little longer, but scoring is very quick. And, test accuracy, right? Of course, this we know, right? They should match the previous one, right? There we go. That's that, right? And also, you can see, F1 score and all the stuff, right? And here, I believe they return, you can get training data. 1 second, let me check something. So this actually gives you more information, right? And then I say, okay, you know what? That's great. Okay, now show me that, average test accuracy. So, here's average. I say CV results, test accuracy, right? Because, that's what it is. Test accuracy, mean. Give me the average, right? So let me check something here for you guys. I want to see if they return training accuracy as well. Okay, there we go. Right, actually, this is good. So they have another option to return training score as well. All right, so let's try this. Okay, so I'm saying, so as you can see, by default, they only return test scores. Right. So here I'm saying return training scores. Right. So see now for every metric, they will return both test and train. So test accuracy is this, right? And train accuracy is this. So what I'm looking for here is I want to make sure, right, there's no big gap. Now, can you guys tell me why I would compare testing and training accuracies? Anyone remember? Why would I care about both testing and training accuracies? Anyone remember? Testing, training. What if there's a big gap? Exactly. Yep. Overfit. Remember? Yep. So if the testing and training varies quite a bit, right? So let me print this out here. Let me do this here. It's kind of hard to read, right? So let's say test accuracy is this. So all right, that's test accuracy, and train accuracy is this. Let's stick with accuracy for now, right? Because that's what we're comparing. All right. So, and you can sort of see here, right? And you can sort of compare the numbers side by side. And you can see, right? I mean, yeah, there's, there are some extreme cases you can see, right? Here and here. But for the most part, right? I mean, they are reasonably okay, right? So actually training should be, right? So typically we actually get, right? But if you constantly see high training accuracies, like 90% training accuracies, and then like low testing accuracy, like 60%, testing accuracies, that's a clear sign this algorithm is overfitting. It shouldn't happen with cross-validation because in cross-validation, you're systematically going through all the data, right? But there are still cases some algorithm will just overfit. Right? I mean, it's just the nature of it, right? For some data, some algorithm will just overfit. So that's why it's pretty cool. You can sort of say, okay, hey, let me compare this and see how they're doing, right? So cross-validate is basically a more, it'll give you more metrics. Now, can somebody tell me why I care about fit time? So fit time is basically training time. Why would I care about that? I mean, it seems like, accuracy and, and also, remember, I don't want to discount the other metrics, for example, like precision, recall, right? You guys understand all this now, right? They all calculate from confusion matrix. But why would I care about fit time? Because my fit time is training time, remember? So some models will take longer to train, all right? And this is something you have to weigh. Like, for example, let's say, a model gives you, that you have a model that gives you 90% accuracy, training time is 1 hour, right? Maybe you have another model that gives you 92% accuracy, but that model takes, instead of 1 hour, let me do an extreme example. It takes, 3 days to train, right? So exactly, right? So, so which one would you pick? So if you think, you know what, I don't care about training time, I just want the absolute best model, sure, then go for the model that takes 3 days to train. But if you say, you know what, 90% is pretty good, you know what, we'll just take a model that's easy to train so we can quickly iterate, so be it, right? So that's why you get the fit time as well. And here it's just, it's just data so small, it's like fraction of a second, right? But if you have large amounts of data, like millions of rows of data, you want to kind of see the fit time also, because you want to understand, right? How the time varies. Yeah. Good, guys. So is that going to make sense? So cross-validation. So what we have done is, we are kind of, even for one algorithm, right? I'm using logistic, right? So on the top few steps, right? I am showing you logistic regression. We are running on like one split. We're sort of advancing from that, right? And then we're saying, okay, I know how to do one split. Now I'm going to do cross-validate. So here we are running multiple tests, right? 5 folds, basically, and run this and get the average. So from this point on, I want your algorithms to be in this format, right? When you get to run algorithms, so don't just do like, don't just do like one run, right? Kind of, so you choose your algorithm and immediately you sort of, do cross-validate. So you don't even have to do, train test split anymore. You sort of see what I'm saying, right? You can just give it a cross-validation and then get the average score. There's nothing wrong with doing train test split, just to make sure, right? I mean, you'll see a lot of code examples, people doing train test split, but remember, that's only one instance, right? So with cross-validation, you are doing a more systematic run. And so whatever algorithm, we learn next, I want you guys to like, basically choose the algorithm and then just, cross-validate it and then print out the, not the average. There are a lot of things you can do here, like people can do like assign weights for their scores, and there are a lot of things that goes on beyond, beyond this. But at least we start to starters, let's do cross-validation, and so this way we have a range. We understand the range, right? So hopefully, I hope this made sense, guys. Any question on this one? Let me look at the chat window real quick. Yes, we will definitely want to get average and also standard deviation, because yeah, RJ, your question, I see that, yeah. And I'll do it in the next lab, because remember the first thing we did, if we just take average can be deceiving, right? So we want to definitely look at standard deviation as well, right? And then that next level, next one I'm going to show you guys. Yeah, good. Let's see. Yeah, compute time. All right, so good. So that's cross-validation. So now we know enough algorithms. We can say, what, yes, even if you use a single algorithm, right? A-base, SPM, doesn't matter. We are going to be cross-validating it, right? And also another cool thing you will see is like, you will see if the algorithm is kind of right, how it's doing, right? If you see like a very, large fluctuation, and I do see it here, right? Like, 50% to 100%. The reason here, I'm guessing, is because the data set is too small, right? We only have 100 sample points, right? So, when you do cross-validation, sometimes, you get bad, bad training and bad testing data. That's why it fluctuates. So if you have, plenty of data and you still see a lot of wild variations, then maybe that model is not very stable. Okay. So this is cross-validation on one algorithm, and this is what we will do, right, going forward, right? Now, what if I have a choice of more than one algorithm? How will I evaluate the metrics? So, and that's what the third notebook is going to be, right? So let me bring this up, right? Open. So here, what I'm going to do is the exact same data, right? I am going to evaluate multiple algorithms. All right, so read data, all this usual, right? So X and Y, right? So basically, you had to come to the point, you have X and Y, right? And, and I've been sort of hammering this point to you guys all the time, right? So whatever the compressed data is, do your shaping, do your encoding, do your cleanup, right? Do your scaling, but come to a point you have X and Y. After that, things are pretty well standardized, right? So here's what you're going to do, cross-validation. So here's what I'm going to do. I want to actually, this is a classifier, right? So I'm going to get a few classifiers. So this is a sample code I picked up from one of the guides. Where was that? Right, so in a guide, I have the cross-validation section, right? And here's one of those. machine learning mastery. Yeah, there we go, right? This one. This is a pretty, right? So, I really like this website, Machine Learning Mastery. This is done by Jason Lee. He really does like very good posts, right? So I can basically, kind of adapt the code here, right, to cross-validation. Anyhow, so basically, right, what I'm doing is, I'm doing logistic, right? So I'm also in KNN, and also decision tree, and also SV. So I think we have done 3 now, right? Logistic and SVM. Let's see if I can do naive Bayes also, just to kind of complete the circle. Gaussian naive Bayes, yeah, okay, let me do that. So what I'm doing is, so right now I'm sort of trying different algorithms, right? So let me bring that, okay, and then I'll add this one as well, naive Bayes. Okay. All right. So I have 1, 2, 3, 5 algorithms, right? So, and some of them we haven't even looked at, like, like for example, you haven't looked like KNN or decision trees just, but but they will go. Let's go with the default parameters, right? That's my algorithm. Then what I'm doing is, right, I'm splitting the data. So I'm saying, run like 10 times. Actually, we should do maybe like 5 times, right? Because 10 may be too much. I say do 5 splits, because the reason I'm doing 5 is I only 100 data points, right? So, so cross-validation score, right? So here's the thing, right? I'm circling through the model, right? Model 1, 2, 3, which is a for loop. You can forget about this. We don't need this for now, right? So all I'm doing is crossval score, model, X and Y, how many CV, right? Scoring metric. What is the scoring metric? Accuracy. That's it, right? Just like the previous one. Only thing we are doing in a loop. Okay, and I'm printing out the results. All right, let's kick this off. There you go, right? So here, each algorithm, I'm printing out the average and also the standard deviation. Yeah. And you can sort of see here, right? 79, 75, 74. Like, yeah. So not surprisingly, logistic does pretty well, right? Let me put them on a graph. It'll even make more sense. This worked for me, but not working here. Give me 1 second. All right. That is strange. Give me 1 second here. Let me go to my. Give me 1 second, guys. Let me bring it up here. So this I'm running on my local machine. So same thing. It's just like some number for some formatting error. So I don't want to spend too much time on this one. Okay, there we go. Right. This is what I'm getting. Right. So let me add my naive Bayes here. That's what I think they're like some version thing going on. Anyway, I don't want to debug this right now, but I'll just add this here. Right. Here's my naive Bayes. So we are comparing multiple classifiers, right? That's it. So you can just keep adding as much as you want. So here I just thought I would just do 5. All right, on all. Okay, there we go. All right. So box plot. Now we know how to how to deal with this. All right, let's take a little larger version. Actually, okay. So okay, sorry, it's missing the labels. Apologies. All right, let me make it a little larger so we can see it better. All right, guys. So now here are the ones. Logistic, KNN, SVM, naive Bayes, right? And ranging accuracy from top to bottom, right? The accuracy range. So what do you guys think? This is pretty good, right? So typically, I'm not surprised here because the decision trees, called CART. They don't score. They give you pretty baseline score, right? They're not the most accurate algorithms, right? SVM does pretty well. You can see here, right? SVM does pretty well here, right? Logistic does pretty well, but it has a large range, 40% to 100%. Same thing in naive Bayes as well, right? KNN does pretty decent. So you can see every algorithm at one point achieves 100%, right? One is 100%. But then then the lowest point is kind of varies too. So let's see what if I do so you did 10 splits, right? What if I did 5 splits? Okay. So this is 5, right? So you can sort of see here, right? We did 5-fold, and you can see pretty much the same behavior, right? So what do you guys think? So looking at this, which algorithm would you guys choose? Which algorithm does pretty decently? Right. So yeah, right. So now at least we have an idea. I mean, they right. So I mean, definitely not decision tree, right? They are kind of they're not doing really well here. So right. I mean, SVM does does okay, right? 60 to 60% or so, right? But also you don't want an algorithm that is which has large swings. So naive Bayes, you can see, right? It's basically doing a doing a large scale, right? So that kind of causes the algorithm to be imbalance, right? And then logistic also kind of exhibiting a little large scale here, right? So KNN is doing reasonably okay. So you can see here, right? But now at least we have an idea into algorithms. Also remember, this data is pretty small, right? I mean, there's only 100 data. I took it because it's so simple to use. You definitely need when you do cross-validation, you need large data samples just so you get an accurate idea, right? So because the reason we are seeing a lot of fluctuation here, guys, for like 40% to 100%, is because the data set is too small, right? So yeah, so don't let that kind of alarm you, right? Yeah. So naive Bayes, you can see also like a big swing, right? 40% to 100%. And this is the median. Remember, the midline is median point, right? So midpoint looks like naive Bayes kind of right? That's slightly better than SVM, but SVM seems a little bit more stable to me, right? Because it's only varying from 60% to 1%, right? 100%, I'm sorry, right? So anyway, but at least now we know. So we're not just like running running one and kind of hoping that's the right algorithm. This is pretty cool, right? So this is basically cross-validation. We are comparing multiple models. And here I'm just only doing accuracy, right? You can change the metric any way you guys want. For example, let's say you think precision is a more accurate description. Sure, change the precision, right? So pretty good, huh? So now, as you can see, now we are kind of going one level above algorithms. So we're kind of comparing multiple algorithms and evaluating, and then going forward. All right. So let me see, go through the chat questions here, guys. The parameter. So remember, when you do cross validation, right? The right. Let me print this out because here. Let me print this out. Oh, print CV results. Okay. Remember, for each run, right, we have multiple numbers. Remember, I'm doing 10-fold, right? So my algorithm is taking the model, right? And then so kind of like this, right? You're kind of like use my Lego as an example, right? So right, imagine like I have like 5 algorithms. Each algorithm gets systematically tested all the way through, right? Exactly. So for each algorithm, I'm not even though I'm not putting it out here, you should see, right? We are getting these results, and that's what is being box plotted here. So it's not like one number they are plotting. They're plotting the right, because remember each I'll get 10 results for each algorithm, right? Because each algorithm you're running 10 results. And that's what being box plotted. Yep. So that's why I kind of waited till we went through a few algorithms so we can do cross-validation, because now the algorithm choice, right, seems a little easier now, right? Because I know a lot of the times you guys ask me the question like, which algorithm should I use? Because we're like doing one by one, right? Now we know a few algorithms under our belt, so we can actually do better. And we can say, okay, yeah, let me give it a try. Right? So there's no surprise anymore. Right? Good. What else? So anyway, so I'm not sure why this is complaining here. Again, my Google Colab, again, there's like maybe like some, yeah, right. So because maybe like some version, something. Anyway, we can look at this. It's not a big deal. SNS. Let me see if plot. Let me see if this works well. PLT. Sometimes Matplot will do that. Yeah. So anyway, so right. So just a matter of changing the plot type a little bit here. SNS. Okay. So something with the Google Colab library version or something. Anyway, so that part is trivial, right? It's just a plot. But you just got the idea, right? That's pretty neat. Oh yeah. So the question was, okay, so how about hyperparameters? Right. That's a very good question. So what you want to do is like, because remember, each algorithm has parameters, right? So what you want to do then is actually called grid search. So there's a cross validator that'll actually do grid search for you. So it's still doing the same thing, right? Now, basically, what you're going to do is you can say, let me see if I can find. I'll go example here. Give me 1 second. Okay, actually, okay, let's go with this, right? So here, what they're doing, right? They're running in a SVM. But remember, SVM, you have a choice of multiple kernels, right? And also there's a Slack variable called C, right? So basically, he's saying, okay, look, try these two kernels, linear kernel and RVF kernel, and also for C, try range 1 to 10. Okay. So here, initialize the algorithm, right? And I'm going to grid search, right? Grid search is now initialize the algorithm and the parameters. And then that's it, right? I'm simply saying, okay, go find the, go with the, go training. So what it's going to do is like, remember, it's going to do the same loop, right? For the model, it's going to initialize the model with these parameters and run multiple tests, right? Here's a right, grid search, right? And it'll come back with say, right? It'll come back with stats. It'll say, okay, we found like using linear kernel with C, C7 is the best model, right? So what's happening? That's the reason it's called grid search. It's basically like systematically going through and searching through every possible combination. All right, that's it. So actually, yeah, this is a good thing for you to consider. So let me actually add this one. I'll add this as homework for you guys. So you can sort of experiment a little bit here. So I'll add this here. Right, solutions. Also bonus lab. Do grid search. Right, and yeah. Okay. So yeah, so this way, you don't have to kind of try different things, one by one. You can just, you can say, here's my range. Okay, go and find the best possible combination. Pretty cool, right? So we are kind of starting to automate things, right? Things a little bit, right? So we are kind of, now we understand the basics, and that's always important, right? And now we can say we are kind of, outsourcing the hard work to the actual algorithm, saying, yeah, look, I know what these mean, but go and find me the best possible combination. Right? So cool, guys. Is that gonna make sense? Again, they're not printing this out the whole thing, but when you execute this, you will kind of get the whole parameters, right? Yeah. I need to look up the calibration curve. I forgot what it was. Let me look it up. Yeah, I'll explain that in the next lab if we can. Yeah. Yeah. Question is like, why kernels? So because kernel choice is just, you can only have a few kernels, right? So it's like a categorical variable. So a kernel can only be one of these guys. Here I'm saying use a range. So this is basically a range, right? So I'm saying, C can vary from, you could have just easily said, C, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Just you can specify all the values. And sometimes, I've seen people do this. So here you can sort of say, C 1 to 10, right? I can do something like this, right? I can say C 1 to 10, but step 0.5. So I'm saying, okay, first start with 1, 1.5, 2, 2.5. You guys get the idea, right? So this gives you a little bit more option, especially when you're doing just numbers, right? You can, you actually want to do a range. And then also you can optionally specify a stepping value, like how far to advance. And the thing is, I've seen people do like a really large range with like stepping value of 0.1. So they'll say start at 0, 0.1, 0.2, right? Because, at this point, you're letting the computer do all the work. Right? So it's not like, you're not sitting in front of the Jupyter notebook and clicking the execute button. It's just like, just let it go and then computer will do the work, right? So you can, and don't make no mistake, this is a brute force approach, right? It's kind of trying all the combination and giving you the best possible approach. And that's what computers do, right? They're really good at numbers. So we say, okay, sure, go do an exhaustive search with all these parameters. Yep, that's what it is. Good guys. So right. So Vasilius, I think you need a bigger, you need a bigger machine. Yes, right. So right. So and this is where people spend a lot of money building clusters and buying GPUs and all the stuff, right? Because right, as the data gets larger and you want to do an exhaustive grid search with like a lot of, and it's very common. I've seen like people doing like serious machine learning. They could spend like just typical grid search might take like 5-10 hours because they're going right, but they'll get a really good model at the end because it's doing all the combination. Yeah, exactly. So, and that's why we when we do this, I kind of I'm using the small data because here the emphasis is not the size of the data, it's just the concepts, right? Good. All right, guys. So let's step back. What have we done so far, right? So we went through different algorithms. Now we understand how the algorithms work, right? And now what we are doing is we are kind of start climbing one level above the algorithm and then say, okay, let me evaluate the algorithm. So at the very least, right, I want you guys to, from now on, even when you're doing a single algorithm, I want you to do cross-validation score, right? Rather than doing like one test train split, we will cross-validate it, even a single algorithm. And then when you get like a project, you say, okay, here's the data, build a model, right? Then you don't want to just settle on one algorithm, right? You actually want to go and evaluate a bunch of algorithms, and you see how easy it is, right? Just that simple, right? Bear with this, yeah, right? Just and here you can just add as many algorithms as you want, right? And you can sort of combine these two, right? For example, let's say, for example, you can say here's SVM, right? And as you're looping through, right? For each algorithm, you can do a grid search if you like, right? So because here I'm just comparing SVM with all the default values. But what if my SVM with like some some kind of different values can outperform the others, right? So now what you're doing is you're doing like a nested loop, right? So you're doing a model, but for each model, you can do like a grid search and then find the best. Like for example, I want to find like the let's say there's a comparison between SVM and naive Bayes, and then let's say they both take some parameters. So I want to find the best I want to find out with the best SVM with the best naive Bayes. So what do we do, right? We have to do grid search on both, right? So as you can imagine, this can get pretty complex, right? Especially when you're like because each algorithm will have their own grid search parameters, right? For example, SVM has kernel and C. Maybe naive Bayes has something else, right? So you need to kind of right? You need to kind of plan this a little bit. So you're doing like a nested loop to basically right? First, find the best algorithm in this class with all the parameters, and then competing with all the other algorithms, right? So it's kind of like imagine like you're at a school. I don't know, you're trying to find the chess champion in the school, right? So what do we do? Like first you have to find every class, right? there's a competition on a class-wise competition. You find the best player in each class. Then they compete with everybody from all the best champions from the other class, right? So kind of like this, yeah. So grid search and cross-validation will do this for you guys. So yeah, somebody said so AutoFeed. No, I haven't used AutoFeed yet. That's okay. I'll check it out. So is it doing a iteration on? Oh, it's doing okay. AutoFeed is selecting feature selection, right? Yeah. So kind of it's basically going through the selecting features automatically, right? You can also look at something called AIC. So feature selection using AIC, right? That's pretty good too. Yeah. So as you can imagine, right? As you can right? And this is what I want to make sure we get to it, because the reason I didn't want to. I've seen people start using cross-validation from day one, and I deferred it because I want us to understand the algorithms first before we sort of go high level. Because a lot of the time when you do high level, you don't really understand the algorithms. It doesn't really register. You're blindly executing some code and just looking at the numbers without really understanding what goes on. But now we have done the algorithms, right? So we're doing feature, we are doing cross-validation. So hopefully it made sense by now. Good, guys. So that's it I wanted to cover. Any questions? Go ahead, guys. We have a few minutes. Any questions? Let me see. Look at the chat window here. What's next week? Yeah. Okay. So, good question. So hopefully everyone caught up. So I'm going to continue on. What I want to do is, so we are here, right? We are the cross-validation, model selection and cross-validation. We are going to go and cover other algorithms as well. So next week I'm going to look at decision trees and random forest, and also things like XBoost algorithm. So we're going to look at more like ensemble algorithms, right? They are very popular. So we are building our algorithm understanding. So next week, I'll set up a reading for you guys to for like mostly trees, like decision trees, random forest, and XBoost trees. Yeah, that's the idea for next week. Okay, I will add something for KNN. Yeah. So KNN is one of the simple algorithm, but sometimes it can be very effective. So yeah, I'll add one of these as KNN. Yeah. So now you guys are getting it right. For example, you can so when I give you a classification task, you have a bunch of algorithm you guys can apply right away. And which one's best? Now you guys know how to evaluate this that as well. All right. So that's what we are building towards, guys. Yeah. I know plenty of people who always use random forest because they're like, what? I know this one works. So I know plenty of people who will only use XBoost, right? And that's fine too, because like in their experience, they have found right this algorithm by far outperforms everybody else. And I'm going to tweak this algorithm the best I can, right? But it's always good to know, have like a good idea of multiple algorithms. So even right, because even when you want to like, there's like at least like I don't know, like at least I know of like 20-30 classification algorithm, right? But you want to have like a short list. And even to create a short list, you need to have some basic understanding of algorithm, right? Which algorithm might do well here, right? So that's what we are going towards. Good. Anything else, guys? Right. So yeah. So if you go ahead and read the cross-validation section here, the ones I was showing you guys are the most straightforward ones, right? Cross-validate, and you can sort of start reading more. Like look at the user guide for them, right? And they'll right? They can talk about combining cross-validations and a lot of other things, right? Yeah. Like I said, you can dive pretty deeply here, right? Cross-validation takes a lot of parameters, and you can sort of play around with those as well. But even if you know the basic CV, right, that puts you ahead of a lot of other people, right? Just the fact you're doing like a systematic search to kind of understand your algorithm, that already puts you in a pretty big lead, right? So, yeah. So these algorithms, guys, right? So now we use algorithms. It's going to be mostly reading, right? Because you use a basic algorithm, basic understanding of how classification algorithms work, right? So yeah, so we'll, and if you find something there's like a cool algorithm came out, sure, right? You should be able to look at the algorithm and say, okay, this is how I use. And in Scikit, you can see, right? It's pretty, APIs are standardized. They are very easy to use. Yeah. So let's see what else. Yeah. So recordings will be, right again, check your, I usually use Slack and also post on Google Group. So when the recording is ready, I'll post the link for you guys. So all the recording, right? So just to make sure, right, you guys are all on the same page. The welcome page, right, for the course has all the recording, right? If you scroll down to the down here, right, each session, right, we actually have a recording, right? All the session we have done is a recording link. So so this welcome page is the one you guys have a link to, right? So this is the link you guys are all using, right? The that link to come to. And then if you look at this, I will keep adding, right, all the information here. So, okay, good, guys. Anything else?
Yes, can I ask a question?
Please go ahead. Yeah.
Yes, thank you. Actually, I want to know if we have a kind of time series data, then the cross-validation would be same as you explained, or how it works?
Yeah, good question. And we will look at time series a little later in the course. But yeah, in time series, when you do cross-validation, you have to be careful, right? Because when you segment the data, okay, I don't want to get too much into this, but when you segment the data, you have to segment the data in the zones, right? For example, because if you randomly segment the data, right, you're kind of comparing event happened on this time to event happened on this time. That it won't work, all right? So time series, you need a little bit of a little extra steps to make this. We'll do some time series later in the session. Okay. Yeah.
Oh, okay.
Yeah.
How many more sessions do you think we will get to that?
So I think, yeah, I'm hoping in the next, maybe, in about 4 or 5 sessions, I'm guessing, right? Yeah, because we are making pretty good headway in the algorithms. So, I want to kind of knock out the popular algorithms, and then we'll kind of do. So the time series, I kind of want to do more like a project based, right? I'll give you just like we did the cross validation. I'll give you some materials and some data, and you guys are going to go and kind of figure out how to do this. Yeah. So.
Yeah, there are a lot of time series algorithms, and I am so confused when I look at them.
That's right. Yeah. Yeah. I mean, yeah, we could do like a one session, just just a one class on time series algorithm alone. Yeah, there are too many, but we'll give you some. We'll give you some, at least some basics to get started. Yeah.
And one more question. I want to know, our class will continue until December and January.
Right. So yeah. So honestly, I haven't really. So we're kind of doing week to week. So maybe I think this might go. I mean, kind of the way. Again, we only have a few more weeks, and also, towards the end of December, we'll take a break, right? It's the holidays, and just right. So we'll take a break. So maybe we will go a little bit into January as well. So depending on what we want to do, right? I want to kind of cover the basics, and then we will take a we'll take a vote and say what do we want to do, and based on what the group wants to do, we will either kind of continue for a few more sessions, or we can bring it to a close. But yeah, but it's very possible. We're already in November, right? So very possibly this will go into January, because last few weeks of December we'll take a break. So
yeah, and that's good.
Yeah. And also, and also kind of on the same token, we kind of want to bring the series to a close as well, right? Right? Because we don't want to just, because machine learning, we can just keep going, for another, right, forever, right? Because there are a lot of algorithms and all this, but we want to kind of wrap up the series as well, so you guys can take a break and kind of, right? We can begin a new series, if there's interest. So, yeah. So
thank you so much again.
Yeah. Good, guys. So that's it. Good session. Again, so hopefully I hope it's been useful to you guys. Keep an eye on Slack and Google group. I will, put in next week's topics. Yeah.
Suji, I can tell you something.
Hmm.
I was doing theory, in machine learning, a course. It was 280 hours. No joke.
I believe this. Yeah, yeah.
I stopped into the 80 hours because I was going mad. I was just thinking, how do you use all these things? What are you doing? What are you trying to make my head think?
Yeah.
Then I stopped and I started actually following you. To be honest, I started understanding what the theory was talking about.
That's right. Yeah.
It was ridiculous for me to imagine that I can just read the theory and try to understand what's going on.
Yep. No, thank you, and I take it as a compliment. And
You
look,
have
I was in the same boat as you, right? Because when I started learning machine learning, I did the mistake of, people, the people come and say, oh yeah, go learn, stats, advanced stats, go learn, linear algebra, right? And then when you learn this theory, it's like very abstract, and you're like, why am I learning this? Like, what's the point of all this, right? So, but the best decision I made is I said, you know what, I'm going to start just practicing the algorithm, right? Okay, I'll go back and look at the theory later. So once I put the practice first, I say, okay, I want to just choose a data set, I want to run the algorithm, and then see what happens, right? Then I kind of understood, okay, this is what's going on. Now, if you really want to understand, okay, the underlying, okay, how the algorithm is working, what's the math behind this, then go look at the theory. To me, that was more productive, right? Because then you kind of have a purpose. You're like, okay, yeah, so I understand how SVM works, right? I want to, I kind of know what it does, but I want to understand how it does it, right? Then you look at the, go look at the math, and then all this, all that will make sense. Yeah. So the theory first approach, I'm not a big fan of it either, because it's just like it's like you're learning for the learning's sake. You know what I mean? Like, there's like no end in sight. So you're learning one theory after another theory, and you're wondering, why am I learning all this? So yeah, so I'm glad this kind of, you found the session useful. And also remember, this session is like a lot of the class people who come to my class, they are software engineers, right? So they know programming very well, but they don't, maybe they've done some math in high school, maybe they've done some math in like college, entry-level math at college, but that's it, right? And then they focus on computer science stuff. So for them, like learning this deep math is, it's not very appealing, right? Because for them, hey, I just want to apply the algorithm, but at the same time, they don't want to just copy paste code and then kind of pray the algorithm works, right? They want to understand, okay, yes, I know how to use the algorithm, I know how to evaluate them. So that's how this class is structured. And this is what, we teach for all of the clients as well, like a very practice-based. So I hope, you guys like the approach, because sometimes people come and say, what's the math behind this? And I'll say, sure, here's a bunch of links, you can go read this. Because the math is, like I said, this math is, easily 30, 40 years old. There's nothing revolutionary in the math, right? It's a pretty old math. It's just like, we are finding different applications for the same theories, right? So, yeah.
The other problem I encountered is some big data sets. So I tried to experiment a little bit with Dask, and I found it somehow useful. But then when you reach to very complex computation things, well, I did try to use PyPy.
Yeah.
And it's not compatible with everything. So it is showing promising, with all sorts of bells and whistles on the advertising, department. But when you really try to use it, it's not what you're expecting.
Yeah. So here's what I want to show you. So if you want, all right, here's what I want to show you. All right. So everything we are doing on a single machine, right? Scikit is a single machine library, right? Pandas is a single machine library, right? All of them are. So right now you guys are here. If you have large data, this is not going to work, right? I mean, what was it you who said your laptop right? Rebooted because of your running yeah. So, large data. At this point, you have to rethink this. So what we had to do is we had to go to cluster computing, right? So So the one of the cluster computing software we use is Spark. And I'll just, right? So if you know Spark, this is an open source package, Apache Spark. Spark has an ML library. They implement the same algorithm. They implement SVM, they implement logistic regression. But the way they do it is all the algorithms are distributed. What do I mean by that? So imagine you have large amounts of data you're running on so that your data is not going to fit on your laptop. So you build a cluster of machine, right? So let's say in this cluster I have 3 machines, but this cluster can be 3 machines, 10 machines, 300 machines, whatever, right? So what happens is your data is going to be distributed across many machines, right? Because your large data is not going to fit in one machine. So data is distributed. When Spark is processing it, it'll also distribute the computing across many machines. So you're running your logistic regression on many machines on maybe hundreds of gigabytes or terabytes of data, right? So that's the next step. And if you look at the Spark, Spark does the same. Like we have the algorithm map here. Let me show you. There we go, right? So if you look at this is the Spark algorithms, right? Same same maps, right? Classification. They're naive-Bayes, SVM, logistic, right? Random forest, k-means, whatever, right? Everything we learned, Spark implements, with a big difference. Their implementation is focused on cluster, right? So let me go back here. Yeah, they are distributed. So these are called, they implement logistic regression, but it's a parallel implementation, right? So I teach a class called machine learning in Spark, right? So our focus is we understand the theory, then we use the machine learning algorithms. Let me show you guys a really quick one. So the algorithm exactly look the same, right? Because Spark made a conscious effort to make it look like scikit-learn. Let me bring one. Let me show you an example, just to kind of you get an idea. So Spark Labs, sorry. Okay, ML Labs, Spark. Okay, so let me show. So let me do one let's say logistic, right? Or like SVM. Okay, yeah, there you go. So college data for SVM, right? So if you look at this, so this is running Spark, right? And you guys recognize the data, right? The admit, GRE, GPA, all the stuff, right? All the stuff, right? Train, test, split, right? Again, we're using the Spark version of this. There you go, right? This is Spark linear SVM. That's it, right? And then see, look at the API, LSVM fit, right? So just like scikit API. And then when you do this, you get something called transform. There we go, right? Transform, right? Predicting the transform. So the Spark API is exact like scikit API, and it's purposely done so because they actually want people moving from scikit to Spark. They want the migration to be very easy. But yeah, same concept. Because once you understand SVM, you understand what it does. It's just the implementation here, right? This training is distributed. So if you have running on a 10-node Spark cluster on let's say 1 terabyte of data, you'll actually run on all 10 machines. And at the end, what are you going to get? You're just going to get a model, right? Yeah. So I would recommend, so a short story, look at Spark. Spark implements the exact same algorithms, and it's very easy to use. If you look at, especially when you use Python and Spark, right? You can, right? The API looks exact like scikit. Yeah. So if you look at, Spark ML, look at some Spark ML examples, and then go to their documentation, right? Look at ML, look at programming guide ML, right? So let's say, say classifications, logistic regression, right? And look at the Python version, right? So right, looks pretty same, right? Anyhow, so yeah, so that's your next step, right? If you are kind of going for large data, don't try to kind of parallelize scikit, because that's kind of right. I mean, that will give you a limited scalability. People have used Dach and Dach and other stuff, but I recommend. I'm a big fan of Spark. It really works well. It's built for this purpose, right? And it gives you pretty good scale. So that's what I would look at. Yeah. So hopefully I gave you some pointers. Yeah. So I always tell people, look, I mean, stop trying to parallelize scikit, right? I mean, you can sort of get that, you can make a little headway, right? If you really want to make the next leap, you should go to Spark. But the beauty is you guys are learning the algorithms. Algorithms are the same. It's just implementation is different, right? Spark implementation, uses distributed algorithms, right? That's it. But the logistic in Spark as well. Anyhow, so I'll stop here. So hopefully it gave you some idea of how to use. All right, guys. So let me look at the chat windows real quick. Right. So somebody said, can we learn deep learning next? Sure. Right. So if there's enough interest, we can start another batch for deep learning as well. Right. So deep learning I teach the same way, like very practice oriented, right? So because deep learning has even if you look at the deep learning math, that's even more advanced than machine learning math. Right, if you can believe that, right? Because deep learning is built on very advanced math concepts. But to use deep learning algorithms, we don't need to go too much into the math, right? They are very easy to use. So that's how we teach deep learning as well. All right, guys, I'll stop here today. Anything else? So keep an eye on the Slack for assignments, and then we'll meet next week as well, right? And then we'll take a break during holidays, and then we'll come back, right? But I do want to kind of bring the series to a close, right? We don't want to just keep going, right? Because I believe there has to be a beginning and there has to be an end, right? And then if there's interest for like a more advanced stuff, we can spin up another series, or maybe we want to go to deep learning or something. But yeah, right. Let's stay focused. So I think we are making really good progress here, guys. Right? We're going to cover a few more algorithms, and then we'll bring it to a close. Okay. All right, guys. Thank you. Enjoy your weekend. I'll see you guys next week. Yeah.
Thank you.